Welcome to the Ricci Flow Nutrition Podcast. My name is Cameron Borg. On this episode, I had the pleasure of speaking with Scott Zimmerman and Robert Fosbury. Scott is an expert in optics and has focused his attention on quantifying the health effects of natural sunlight. With over 35 years of experience in the industry, Scott has unparalleled knowledge about how light interacts with systems. Scott is now a world leader in the optics of the human body and how light interacts with life. Bob is an emeritus astronomer at the European Southern Observatory and an honorary professor at the Institute of Ophthalmology at University College London. He's an integral part within the Institute of Ophthalmology with his unique perspectives on light and its interactions with the Earth's atmosphere. His work with Professor Glen Jeffrey has paved the way for a new understanding of how light, particularly in the near-infrared range, interacts with the human body. His physics background has proved indispensable in understanding sunlight and how biological systems have evolved to use it. This is quite a special episode for me as it's the first time I've had two guests on at the same time to discuss their work together. Both Bob and Scott have come from well outside their respective fields of astrophysics and engineering to view the biology of the human body and its unique relationship with light in a way that it was not previously been done. To me, they represent the perfect examples of why interdisciplinarity is so incredibly important, particularly now. Bob and Scott are contributing greatly to the understanding of biological systems and are continuing to use their wisdom to positively influence the future of health and lighting. To frame this conversation in as brief a manner as possible, Scott and Bob have both independently come to the conclusion that the human body, at its core, is a light harvester. Not only do we exhibit all the characteristics of a system that captures light, we funnel this light deep within us to allow it to perform as much work as it can. Our moving inside, away from the influence of natural sunlight in the last 100 years, is the core of our modern disease epidemic, and until our doctors and practitioners take light seriously, we will continue down dead-end roads and never make any progress. It was a real honour to speak with both of them. With all that being said, I hope you enjoy the episode. Maybe we can start a little bit just talking about what you guys are working on at the moment. And just maybe a little bit of background on how you got there. Maybe you can start, Scott.
Well, I mean, I'm an optics guy, basically. And I started looking around at all the stuff going on with photobiomodulation. I was looking to generate a new light source. And I looked around at the photobiomodulation stuff and all the work that had been done by Hamlin and interviewed him and talked to him a bunch. But I came to the conclusion that we really didn't understand how the optics of the body. I mean, it's kind of surprising, but there really is very little out there as far as information about how light propagates in the body. Everybody kind of assumes they talk about penetration depth, but as you know, you saw some of Bob's pictures. You know, penetration depth makes no sense in the near infrared because light propagates and distributes inches into the body, and bounces around, and it's actually localized in the blood vessels from an purely optical standpoint. And it's really quite amazing. And then I started looking at the optics of the eye and optics of the brain, and you start seeing how in the near infrared, you know, you're getting all kinds of light channeling effects, what we call light guiding in the optics industry, and where the body is going to great lengths to propagate near infrared down into various tissues, including, you know, the gray matter, the retina. Actually, most of the light that goes through to the retina actually passes through the sclera, which is kind of amazing because you got an optical element that's amazing imaging element, but then it's also a non-imaging element in the near infrared where it's actually collecting and guaranteeing that there's always an excess of near infrared on the retina. The same thing holds true as we've talked about with the fetus in the womb and how the mother's skin actually filters out everything but the near infrared through the early part of the pregnancy. And then as pregnancy progresses, the skin stretches and it expands the spectral range that the baby is exposed to, or the fetus is exposed to until birth. And you know, the more you dig into the optics, the more you figure out, hey, you know, this isn't just by happenstance. This is, you know, near infrared represents the largest portion of the light of the photons that we actually absorb. And that's especially true when you walk outside, because you get this amazing effect where the fact that we're standing vertically, the solid angle that of most of the energy that's actually, our photons that are actually put in, absorbed by the body, are actually coming from our surroundings, because it literally absorbs in the visible, but it reflects in the near infrared quite strongly. So the more you look at this, and then so this was all part of a methodology where I was trying to understand the optics, and then once I understand the optics, then we started looking at, okay, what do those photons do? And you can get a kind of a gauge of that using some of Zastro's work from electron spin resonance to show how what the free radical distribution that light is causing, or those photons are causing. And then the final section, which is what I'm working on now, is okay, we know the free radicals are there, we know the rate that they're there. Now, what is it the body's doing to respond to that? And that's where you come into melatonin and all the other hormones and antioxidants response. And what you get out of this whole thing, in a real summary, is that what we've developed is an artificial environment that we spend most of our time in, that actually pushes or favors cortisol and stress hormones, and creates this situation that, because the way the body's set up, hormones work in opposing pairs. Cortisol and melatonin are supposed to be in opposition to each other. But what we're starting to figure out is it's a whole lot more complicated than that. And that, it depends on the situation. If I'm in a sedentary condition like they measure for circadian, then cortisol is high in the morning, melatonin is high in the evening. It's pretty straightforward. But the minute you actually do something, and the reason they do sedentary is because the minute you do exercise, any of these things called life, all of a sudden cortisol and melatonin go up together. Because what's happening is the melatonin is controlling, cortisol is a great hormone, it's important, but if it gets out of hand, you got real problems. So what appears to be going on, based on the transient work that we just got published in biology, is that as you're moving those two up together, melatonin starts to shut down or suppress the cortisol. So that's kind of where it's kind of been this kind of like 3-stage thing that I've been working on in this discovery. And what's really exciting is that, it's starting to make some sense. I guess is what I'd say. And it's starting to link into some of the things that we see in our modern society, the stress levels that people are feeling. Yes, there's other kinds of issues associated with social issues and all that. But in reality, there may be a physiological thing. We are inducing an extra level of stress that isn't necessary. And especially when you start looking at some of the maladies and things of that, different types. But anyway, that's mine. I'm sorry for the long discussion about it, but
No, that's great. It's a great little rundown of makes it sound like you did all of this work in a few nights, but this has been quite a long road, I think, with your research. Um,
yeah.
I guess maybe we could just even more briefly summarize that to essentially we've found ourselves in a situation where our environment doesn't match our evolution, and our body is, exquisitely designed to harvest and point near infrared photons in certain directions to basically do work in the body and maintain homeostasis and make sure we're staying healthy. And this environment that we've created is not conducive to that at all. And the ramifications of that are very far reaching, and they don't just manifest themselves in one disease or one particular type of malady. We're getting all of these diverse types of responses, and there's likely nothing that's not being affected by, I guess, our lack of near infrared light. Is that a pretty succinct summary of what you've been looking into?
Yeah. And I think that one of the things that people don't, it's very hard to measure. the ability to measure some of this stuff is we found this the work that where you there's very few there's probably about four papers in the entire lit where they actually measure the effect that light or exercise or anything has on hormone levels in real time during the event. Entire circadian theory is based on, what's going to happen 4 or 5 hours later. It's not that's true. I'm not arguing about the circadian, but our ability to measure is now changing with all these wearable biosensors. And what we're seeing is it's moving around in ways we didn't think it did as far as the hormones. And hormones are, like I said, I've been looking for what's the antioxidant, what's the response. I mean, you can say blue light's bad and what we're doing is bad, but okay, what does that physically mean? What's the mechanism? And I think that's what we're kind of on to now, where because it takes very little change in hormones to have a huge effect on a lot of things. And melatonin seems to be a very key element, in this whole process. So,
I mean, it stands to reason it's one of the oldest molecules we really know about, so it makes sense that it's quite deeply rooted in our physiology. Um, Before we
yeah.
move on to Bob, I wanted to know, have you read Fritz Holwich's book, something to the effect of the influence of ocular light on metabolism in man and animal, or something like that?
No,
It's
no.
a it's an old book. It's like from the 40s, I think. Holwich um wrote this, and it's all these old school studies on the influence of light on animals and their hormones and their blood levels. And there's basically a chapter for its effect on the liver, its effect on the kidneys, and it's really fascinating studies from the 20s and before.
I like the old stuff.
They learned from the Victorian hospital matrons who wheeled people outside. I mean, they did know this 100 years ago. They knew this stuff.
Yeah. And the reason I like these old studies is because they actually they use sunlight instead of, doing all of the stuff in a lab. They actually got animals out into the sunlight, and they were controls in the sun, and they would keep some animals, completely in the dark, and have a look what would happen, and they'd cover their eyes. And it's very different to the kind of studies that are done today, where everything's inside of a lab. The control animals are in a lab under, fluorescent tube lighting. It's hardly a control really. But yeah, this book is I like the old stuff because it seems like they got a lot more information out of it. Maybe they didn't know why, but they knew that it worked.
Oh yeah. I mean, and you look back at what they used to do in hospitals with the old pavilion style, where they
Mm,
would bring people out and let them be exposed. They didn't know why it was doing it. And that's kind of what I've been trying to focus on is what's the mechanism?
yeah.
And, I totally believe in that, blue and UV and all that. It has it's such a high energy photons that they can do random damage in ways that the body can't predict. So the body had to have some mechanism to deal when you start calculating the number of free radicals generated and how they're distributed in the skin. You look at it and you say, holy cow, how in the heck are we even alive? And, what you start to see is that it's the role of melatonin is an amazing antioxidant and all its metabolites that go along with it. So, there has to be some antioxidant response of some type. And, what appears to be happening is that, that it's occurring um, in in the cells in the mitochondria itself, that we're actually producing the melatonin in the mitochondria, and that is part and parcel of just daily life for a cell. I mean, it has to have the ability to deal with the free radicals that we generate. It doesn't put down the pineal gland in any way, shape, or form. The pineal gland, melatonin was selected by evolution to be provided by the pineal gland during times of low cellular activity. and pump in a bunch of antioxidants so the brain can operate at 80% of what it operates during the day. I don't think it then is very surprising that the mitochondria would do the same thing for the nucleus, where it's literally generating an antioxidant response to help protect the nucleus. It's really kind of like the same thing. And you can kind of look at it from the evolutionary standpoint. You start out with a cell. We know that melatonin was hanging around there for billions of years. And then the cell got a little more complicated and developed the ability to start detecting light in the melanopsin in the skin area or in the outer surface. And then they went to making eyes, and eventually we got to the point we have a pineal gland that's allowing the brain to operate at a much higher level than it could without it. So, and melatonin's been in that route. Now, there's other, testosterone, there's all kinds of hormones that are being affected by sunlight. It's just that this one is the one that we actually have some data on, and it's very limited data, but it seems to indicate what's going on. So
Yeah, I mean, it sounds to me like there's a very beautiful story emerging from what you're speaking about, this this unifying idea about how light sort of connects all of biology together. So I guess with that, we can jump over to you, Bob, and what you've been doing recently. I'm sure there's been an update since we last spoke with you and yours and Glen's work with this
Yeah, I'm
kind of thing.
almost totally exhausted at the moment, actually. There's so many things going on. First of all, I'm trying to listen for things that Scott and I can disagree on, and I haven't really found anything yet, but maybe we'll find something, and it'll become interesting then when we find something. But no, I in a way, I've been coming at this from a different direction. I think we've ended up very much in the same place, but certainly I've come to it from a very different direction. And my approach has been rather different from Glen Jeffrey's as well, my collaborator in UCL. I mean, we argue about these things from different perspectives, which is very productive, I think. But I think, yes, if I summarize the way I've come to this is it's a little bit of it's a post analysis of the way that we've come in this direction, but it's really based on my astrophysical background, where I tend to look at things on a rather big scale, talk about planetary scales and stellar scales, and the origins of light and what the light looks like and how it would look like in different planetary systems and so on. But I think the productive idea was to think, well, we know that solar photons essentially drive life on our planet. I mean, that's not completely true, but most of the life we see around us and talk about, certainly the solar photons are by far the predominant source of energy driving the life. And it seems to me we've come along this route, and we understand pretty well how the chemical energy is produced from solar photons through photosynthesis, which is an exquisitely complicated process, wonderful magic going on in these chlorophyll molecules and so on to split water and so on. Wonderful process, very physics rather than biology, I have to say, but it took 250 years or so to figure out what was going on. And we still don't understand all of it. But the basic principle there is you're starting with photons coming from the sun. It has to come through the atmosphere, which does a bit to the spectrum, but not very much. Basically, sunlight reaches the ground, with the exception of the ultraviolet, of course, which at the moment we'll forget about everything below 300 nanometers. It's all absorbed by ozone in the atmosphere. But the sunlight, the visible light that we see, and the infrared light, to a certain extent, at least the near-infrared light, is relatively unhindered by the atmosphere. So we basically get sunlight on the ground, a bit diminished in brightness. And that sunlight works through photosynthesis in cyanobacteria and plants to produce chemical energy in the form of sugars. And it's brilliant the way that it does it. But basically, you have solar photons going in, and that energy with some efficiency, which is not terribly high, but high enough to do some good, gets converted into chemical energy. And that either gets eaten by the rest of the biosphere, or it gets stored as stuff which ends up as coal and oil and all that stuff. So all of that stuff comes from photosynthesis, basically. So solar photons really are the ultimate driver of energy. And we know that life is a very low entropy process. It fights disorder and it fights disorder. In fact, it exports disorder, and it tries to do things in as low an entropy way as possible. And that's a guide to us to try and understand what the solar photons are doing. And it's a focus for asking questions about what is this light doing if it's being used in a low entropy fashion, which we would expect for life. So the photosynthesis tells us a lot. It tells about where the energy is coming from and being stored as chemical energy. But what about the rest of the biosphere, that perhaps much of which eats the sugars that are being produced by plants? What do they use light for? Well, the obvious thing, and is really the stalling point, I think, for most people's thinking, they use it for vision. Animals can see. And in the Cambrian explosion, animals suddenly, we can make eyes, we can be predators, or we can avoid predators. So there's a natural process of very, very quickly evolving vision. And I think, my look as an astrophysicist, looking at what all the biologists are doing and so on, they've somehow forgotten something, because, it's not just vision. There's other light out there, which is perhaps invisible to animals and us. What is that light doing? So I would ask the question to the biologists. We've got light beyond the range of vision, say beyond 700 nanometers in the near infrared, before it gets all soaked up by water, which is, call it what you like, 1 micron, 1300 nanometers or something. The water gradually absorbs. What's happening to that light? And the evolutionary biologists will say, well, sure, life will use that light because it's there. It's a source of energy. It's a source of process of life. Therefore, of course, it will be used. And what's it used for? And then you look at the literature, at least 10 years ago, you look at the literature and say, well, so what's it being used for? We don't know. One or two ideas, perhaps. The Victorian matrons knew about it, but they didn't see it in quite the same language. So I think that was the thought that I had. What will life do with the near infrared if it's not using it for vision, but maybe using it for other things? And this is where we come into the same territory. And I suppose, again, my big realization was that actually living tissue, plants and animals, in fact, almost all living tissue, is remarkably transparent in that region. I mean, it's almost completely opaque when you get below 600 nanometers or something in the red. But between that and 1300 nanometers, it's actually rather transparent. And I see the analogy with the leaves of plants, which are, of course, opaque in the visible because they're busy absorbing visible light to make sugars. But beyond where photosynthesis occurs at around 680 nanometers, the plants think, hey, this light, I don't want this light. It's actually making me hot and making me lose water. So I want to get rid of this light as quickly as I can. So you look at leaves of plants, and they're incredibly reflective in the near infrared. They just want to get rid of that light as quickly as they possibly can. And I've argued with the biologists or the botanists about this. I say, look, do you realize how efficiently plant leaves reflect infrared light, near infrared light? And they said, they don't often look in the infrared, I don't think. But yeah, we know this. We look at infrared photographs and we see the leaves are brighter than the white clouds sometimes. So they have a very good mechanism for getting rid of this near-infrared light. And perhaps anthropomorphically, I think they're donating it to the rest of the life on the planet. They don't need it. So they're saying, hey, guys, we don't need this stuff. Why don't you use it for something? And so life has evolved to use that light to do something interesting. And I guess the other realization I had, was very closely related to the thing Scott's been thinking about for a long time, and that's body optics. I was fascinated to see what you guys were doing on body optics. I mean, I knew a bit about the brain, like getting into the brain, but just the idea that the body was working to make an optical system that captured light and got it into the body was really a new idea. And I recalled, I have two analogies. One is a rather scientific analogy, and that's some years ago, I think it was around 2014, I decided to observe the light coming from a very dark thundercloud with my spectrometer. So I spent a long time looking at this thundercloud. It's quite faint light, but I integrated, I did lots and lots of sort of time lapse with the spectrometer and collected light from the thundercloud. And I looked at the spectrum, and I'm very familiar with the spectrum of the atmosphere. I spent the last years of my life doing it. And I thought, well, this looks really strange, because a lot of the very weak absorbers you only see when the sun is setting on the horizon. A lot of the weak absorbers appeared very, very strongly in this thundercloud spectrum. And yet the sun was at 45 degrees, where you would never see these lines if you were looking directly at the sun. Something was happening when the light entered the thundercloud between entering it and coming out the other side. And so the obvious answer was, well, this light is bouncing around between particles in the thundercloud, probably mostly water drops of a whole range of sizes. So it's bouncing around between water drops. And sometimes it'll go through the water drop and it will absorb some of the near-infrared light just in the water vibrational absorption spectrum. But often it'll reflect off the water drops and be a lossless scattering, essentially, an elastic scattering process. And it turned out when I modeled these weak absorption lines, they're actually the absorption lines you get when you have collisions between two oxygen molecules. Now, I don't know if you know about this stuff, but in the atmosphere, you get things called collisionally induced absorptions, where if you get two oxygen molecules coming together, they interact with Coulomb interaction, and they'll bounce off one another. But while they're interacting, they're distorting the energy levels in the other molecules, and they're removing some of the degeneracy in the quantum states in the energy levels of these molecules, and they're allowing transitions to happen that don't happen in undisturbed oxygen molecules, and they're called CIAs, collisionally induced absorptions. They're actually responsible for a small percentage of the global warming. If you compare them to carbon dioxide or something for global warming, these collisionally induced absorptions are there at a level of a few percent. So they're of great interest to the atmospheric physicists. But these collisionally induced absorptions, you see them very clearly when the sun is low on the horizon. In fact, if you use a visual spectroscope, which I always have next to my right hand, this one here, if you use a visual spectroscope on a setting sun, these collisionally induced absorptions are the strongest features in the spectrum. And they were recorded by Angstrom when he first studied the telluric spectrum of the sun a long time ago, but he had no idea what they were, but they're marked. Some of them are marked in his maps as unidentified features. Now they're well understood. Anyway, the light coming out from my thundercloud, and I've got this on my Flickr site, actually, the light coming out from the thundercloud had very strong collision-induced absorption lines, as strong as they would be if the sun was on the horizon. And, I thought about this for a long time, but when I started thinking about the transparent body, it struck me that this is exactly what we're looking at in our transparent tissue. We're getting light into the tissue. It's scattering around between cell walls. Any sort of refractive index, inhomogeneity and so on will scatter it. But the absorbers in that range, the molecular absorbers, are weak absorbers. So you have to travel quite a long way within the tissue before you get your photon absorbed by one of these molecular absorptions that we find in this transparency window. And it was a sudden realization, because Glen and I, for a long time, been looking at mitochondria, looking for strong absorbers in mitochondria. And there is a strong absorber, and that's in the Soré band in the visible, in the blue, at 420 nanometers, very strong absorption. partly from the heme, probably partly from the cytochromes and so on. But it's a very strong absorber in the ultraviolet. But then we looked into the red. We had samples in little 1 centimeter cuvettes. It's a very small path length. And so we didn't see any absorbers in the infrared. And we got very disappointed because, we knew that mitochondria were interacting with infrared light, but we couldn't see the absorbers. And it suddenly dawned on me that it's because it's a weak absorber. And that's the whole point. They have to be weak absorbers. If you have strong absorbers, you never get the light in. So the light gets into the body, and it has a chance by scattering around, doing a random walk through the body. It gets a chance to interact with one of these weak absorbers, which are the important processes concerned with respiration. So like blood and cytochrome C and the electron transport chain, and perhaps a few other things which we've not necessarily recognized yet. So this is a machine. The transparent tissue is a machine that basically captures a photon gas. The photons get in, and they work. It's just like a gas. They bounce around like molecules in a bag of gas until they're absorbed by something. And this is your body optics in a way. There's nothing fancy. It's just the fact you capture all the photons in this volume, and they stay there much longer than they would if they went straight through. So it's a light trap. It's
even more from the optics standpoint. Just quickly, is that what I found is when I started modeling this diffuse volume, it's very hard to act. One of the hardest measurements that you can make in optics is to try and actually characterize a diffusive volume.
I know.
It's non-Hamiltonian. It's a lot of stuff going on, but when you try and get what you see is this amazing effect of it's. I liken it to, if you ever gone out and seen a snowdrift around where they piled up from an asphalt driveway or parking lot, and the sun shines on it, and eventually what you'll notice is that it gets darker and darker because more and more of the black asphalt particles are absorbing. And that's exactly what happens in the body from the standpoint. It bounces around, as you say. And what happens is that the location, what it does is if you actually do the model, you see that it actually bounces around and eventually ends up in the blood vessels, because that's where there's a strong absorption point. In your picture, you show that, that absorption has been shown by various people to increase blood flow by causing a vasodilation of nitric oxides and things of that nature from the free radicals that are generated by the near infrared. So what happens is that literally the body collects and distributes it throughout as far as it can, so by bouncing around, but localizes it in the blood vessels so that you get this added effect of removing more trash, essentially causing more blood flow, bringing in more various macrophages and things of that nature. So to me, it's a where we kind of join up on this whole thing. But
no, it's a fascinating, slightly different perspectives, but we're actually looking at exactly the same phenomenon. And if we look at the spectrum of this, the spectrum of a human body in my hand, for instance, I looked at the spectrum of what's going through my hand. You do see a number of absorbers, and one of them, obviously a strong one, is the deoxygenated hemoglobin in the veins. Notice you don't see the arteries, really. You just see the veins. You don't see the bones, which surprises the biologists. They're almost essentially as transparent as everything else, which is fascinating.
I don't know if you've had a chance to watch any of Roger Seaholt's videos.
Oh, I have. Yes, I'm a great fan. Yes.
Yeah. Well, he's got the one where he said, as you say, the old way. They used to take a red light, stick it up against your neck so that they could see whether or not your sinuses you see various things, because you could literally, if you listen to the literature, the optics guys that are out there, most of the thing, they say, oh, it only penetrates a millimeter. Well, how come I can a kid who's told a ghost story and stuck a flashlight up his nose, up in his mouth, it can tell you that it's going a lot farther than just a millimeter. And, and that's just the red edge we see. It's not the near infrared component that extends way out. And, like I say, I just think it's fascinating how the body, as you say, uses the entire solar spectrum. And we just threw it away because we couldn't see it. And
evolution will not allow you to throw it away. And I think if you think of this in terms of entropy, if you have these infrared photons coming in, if you're going to just absorb them as heat somewhere deep in the body, that's a high entropy process. If you convert them into energy, into ATP through the mitochondria, you can use that energy to move things around. You can use that energy to think with, and do cosmology with, if you like. That's a much lower entropy way of tracing the solar photons through. They're always doing something useful. Evolution will always do something useful.
Yeah, well, one of the things that I kind of actually a little proud of is that when we started doing the calculations of free radicals generated by various wavelengths. Zastro did this great work where he took a ton of skin samples out and he exposed them to very narrow bands of different wavelengths and throughout the visible and into the near infrared. And what you found when I took the data, he was looking at it from a standpoint, he was actually worked for a cosmetic company, and he was trying to look at how to make better sunscreens and things of that nature. But when you take his data and you invert it and look at it, the average number of photons required to generate a free radical, all of a sudden out of his data drops every one of the water overtones, 7 of them in the data. Wasn't looking for it, didn't expect it, whatever. But what it shows is near water absorption bands, you get an increase in the free radical generation rate at those particular bands. And there's a ton of bands throughout the near infrared into the farther, as you say, farther out. And what it shows is that our understanding is a little bit off as to what's going on in those regions. And you also, once you start doing that, you start seeing that the UV, the visible and the near infrared are generating equal amounts of free radicals compared to the UV and the blue. It's pretty straightforward calculation. But as you say, what I liked about one of your comments was that you were talking about the need for blue and red together. And I think that's where we really agree is that I believe that in nature, we're never exposed to blue and UV light without photons, without an excess of near infrared photons. And I believe that that's because the body's using the near infrared to set up various protections, because it cannot determine if a photon, 480 or 300 nanometer photon is going to crack a molecular bond, and you don't know which one, because the body couldn't do it. So the body has developed a system where we change out our skin every 20 days, and we're flooding that area with, if you look, part of the studies the things that we found is that they're starting being able to measure hormones in sweat and other types of things, and you start seeing that where melatonin's coming out onto the skin, getting reabsorbed into the skin. You've got all these other effects going on in the skin, and it turns out that the skin is actually is capable of generating basically every hormone that we do internally, but it does it locally, and that's being driven by the fact that the free radical generation on our skin is so high from UV, and it's so it's all localized. The blues and the ultraviolets are being absorbed in a very narrow band of the skin, that you see that there's all this stuff going on. Anyway,
I think all the experiments that Glen and his people have been doing over the years now show that this balance between the blue and red is really necessary. One as soon as you put those out of balance, then you're in trouble. You can certainly mitigate the effects of lots of blue light by using red light and near infrared light. So
yeah, and I guess my the only thing where I maybe disagree with you is that I believe that there is not a healthy solution with visible only light, photons, systems, and that you need the near infrared component because it's doing other things we don't even know about yet.
absolutely, yeah, I don't disagree with you over that. No.
Oh, okay. Yeah, no,
Not.
it's concerning to me that the industry is slowly starting to move and accept that there's something going on. But the solution is we're going to put red lights everywhere at night, and we're going to, everything. I mean, we're turning everything into a bordello, a bordello, and it's I'm not convinced. I mean, there seems to be this separation where we're meant to see from in the visible spectrum, but this other part, if I keep on saying, if we could see in the near infrared, we'd lose all our ability to differentiate between an apple because everything would be flooded with,
Light.
be white.
Yeah.
And now we have this opportunity to put back to restore the near infrared, and everybody's trying to do it halfway with a little bit of red, is my opinion.
We've Glenn and I have had very interesting conversations with architects and lighting engineers. We had a meeting with a very, very big multinational company of engineers, of ecologically friendly engineers. I better not mention their names at the moment, but they're very serious about this, and they have. We talked to their chief lighting person, and they're extremely interested in this stuff, and they get it. I mean, the person we talked to had a PhD, and she'd worked on glass transmission.
Oh, really?
For buildings and so on. So she really knew about this stuff, and she was absolutely fascinated by this. And we're having more meetings with these people, and they have a huge influence on the building industry. They're involved all around the world on some of these very innovative building projects, ecologically friendly building projects. So we talked about, infrared rejecting glasses and how dangerous they would be for health in buildings. We talked about the influence of trees on reflecting near infrared light into buildings. And indeed, we talked about the artificial lighting as well, of course. And I think I mentioned your idea of using, a combination of LEDs and filament lamps to get a much better spectral fit to what we think is healthy. So, and these people are serious about this. And Glen is actually getting them into his lab and doing experiments on the individuals involved in doing this to see if he can improve their vision, which makes them happy. But they're taking this stuff very seriously, I think. And companies like this will have a big effect. Companies like this will have a big effect on influencing lighting companies because they'll be the people who are specifying the internal lighting. Yeah. So I think this is very interesting, the way this is developing.
Yeah.
Well, it is amazing how we've managed to go from a situation where we're always exposed to near infrared, to a situation where we have zero near infrared. Mm-hmm. And I think that's the dichotomy, or the issue is that we didn't just take a little bit away, we took it all away for a lot of people, especially I think the recent study showed that people in some nursing homes get 5 minutes of sunlight a month, So
I saw I just glanced at one of the diagrams in your write-up, and I saw something about this, and I thought, yeah, that's very interesting. You had various hospitals and surgeries and care homes and so on with the integrated amount of infrared light. Is that right? That's what I didn't have time to look at it in detail. But
the point is that when you start quantifying, there was this really neat study that they did where they put a near infrared vest over 10% of the body, made this vest, and it covered 10% of the body. Mm-hmm. And I think that's one of the things that people don't get is that unlike your eye, where it comes through a little, you're talking about the surface area, the volume of cells that are being engaged. And you're talking about 10 to the 17th mitochondria that are sitting there. And they're all, so you can have a huge effect with that. But just putting back even a 5 kilojoules worth of near infrared showed used via this vest caused a 4-day reduction in time in the hospital. Now you can look at that.
This is the Brazilian experiment that Schultz talked. Yeah, I know that. Well, that's a brilliant experiment.
It is, and but the question is, it's always the issue is it a question that the treatment made them better, or was the hospital so lousy, causing them to be sick? And I would argue that it's really quite easy to generate the levels of get significant near infrared into these hospitals. And why don't they actually measure the hormone levels? Because we know that melatonin and cortisol will, you get a fever in the evening or afternoon because your cortisol levels are dropping, because high cortisol tends to suppress the immune system. It's important to do, but it suppresses the immune system. So what ends up happening is that, we've got going into this environment that literally in hospitals that literally is suppressing the immune system in the hospital. And I'm kind of going, this doesn't seem like what you want to do in a hospital. And,
But Scott, this is so obvious to us. I mean, you look at a hospital. I was in hospital recently because I broke my leg basically at the end of July, and so I was in hospital, and I was thinking, Jesus, I'm not getting any near infrared at all in this room. And if you're sitting for a week in a hospital bed or in an intensive care unit, you're getting no near infrared at all, and it must be extremely unhealthy to do that.
Well, and to be honest, I started out working on this stuff for lighting. And then my granddaughter, she came down with neuroblastoma. And so I converted over. My wife and I have spent a lot of time and money trying to understand the effect of light on cancer. And there's some really great studies out there now that are associated showing that melatonin suppresses glioblastoma and all these other things. And there's some work done in Germany and other places where they're showing that not to stop, it's complementary to have the near infrared with standard treatments, and it's complementary. They got multiple studies out there. One that shows that near infrared helps with preventing you rejection from the chemo, and then they got melatonin treatments that are, and I'm saying they're the same thing. But trying to get the medical industry to look at light as a therapeutic device is very difficult. And people like Roger is really starting to push it a little bit more. But, all I'm saying is that we are controlling our immune system based on how we're exposed to lighting. And why would we make it harder on the body rather than helping the body? So,
well, just while we're talking about Roger, I mean, I'm a great admirer of his videos. I think they're great. But one thing that I don't have his email address, so I haven't written to him, but he talks about most of the energy of sunlight being in the infrared, which is not true. It's most of the photons that are in the infrared. That's what he means, but he says energy. And as a physicist, I find that disconcerting.
Well, okay, I'll be defensive here. When he makes that statement, and if you look at some of the graphs you're doing, if you look at how light, the photons that actually enter the body, the majority of them and the energy is significantly higher in the near infrared, because you're basically walking around in an integrating sphere where the light reflecting off the leaves, it's really kind of amazing, because the fact that we walk upright, you look at the solid angle that comes into the body from sunlight, this sun source, is about 50 times lower than the solid angle that's associated with all the reflection around us. Now, and on top of which, if you're wearing even light clothing, it's blocking the visible, but it's not blocking a good portion of the near infrared because it's penetrating. So in Roger's defense, I think what he said, I'm probably the one that has made him make that statement, but I agree with you. If you're just, one of the pet peeves I have is that, everybody wants to go to ASTM 1.5 type spectrum of sunlight. And in that particular case, yes, you're right. There are more photons, but there's equal or the same amount of energy. But when you get in the environment that we are adapted to, it's actually the fact that we are vertical. We collect from a much larger solid angle than you do from the other, and that's what.
Okay, I'll go along. I'll go along with that. That's fine.
Well, at least we tried.
I'd love to just jump in here and do a little bit of a recap of what we've touched on so far. So I think what's been so delightful talking to both of you independently and now together is that you both sort of come to this conclusion that basically our bodies, and I'm sure other animals as well, are exquisite sort of light harvesting devices, and we not only capture but we funnel the light to make sure we're using what nature has to offer as best as we can. And that's really quite fascinating to me, because you're right, it's very difficult to get this story about light across to the practitioners across in the medical field, where light kind of seems a bit silly, I guess. Why would light work? Why would light be an effective treatment for anything?
It's too cheap. It's too cheap.
Yeah, well,
I'm being critical here.
Without going down that rabbit hole, because that is a very, very big rabbit hole. But I mean, the point is, in the last probably century, our light environment has changed beyond comprehension, really. And I, on maybe some of my more wild thinking days, think that that's probably the primary reason we've got all of the chronic diseases that we have today, is that our light environment has changed, more than our diets have changed, more than our exercise habits have changed. The light environment has changed substantially more, and that's, Occam's razor. We should look at the things that have changed the most to explain the changes in health patterns. That's what I think anyway. But basically, we are light harvesting devices, and we use that exquisitely well to harness all of the power, all of those photons, and we've basically lost that in our environment. Like Scott said, it's not like we've reduced it by 20% or 50%. It's a complete different environment. It's a totally alien environment for us. And the worst part is it's invisible, so we can't really make sense of what's going on a one-dimensional level. So that's sort of where I see where this discussion has sort of where you guys have sort of come to the same story from two very different points of view, which is really fascinating to me.
I have a question. I have a question for you, Cameron, on this very topic, because
Sure.
Glenn and I have discussed. We're understanding this stuff, and we're seeing the problems, we're seeing the issues, we're seeing some of the solutions. How do we get the message out there? This is the problem. We write a scientific paper, it's read by 50 people, if you're lucky. How do we actually get, and you guys are getting the information out there. You're one of the ways of getting the information out there. And, we thought about this, and this is why we thought about the architects, because, these architects are interested in building buildings that are healthy to live in. And so they want to know this. The lighting companies will want to know this at some point. At the moment, they probably don't want to know about it because, they've got the market. And but if the people are specifying what they have to produce, the regulators, the architects, the lighting engineers are saying, look, we want something different, then it will happen. But we have to get the message out there. So we collectively need an understanding of how we most efficiently make this knowledge available to people. Now, whenever I talk to anyone, I had my my hairdresser this morning is a very interesting and interested young lady. I talked to her about, I mean, she's interested in wildlife, she's interested in gemstones and all of the physical things that I'm interested in. And I tell her about this work we're doing. She's absolutely fascinated. So then, it's not difficult to get this idea over. It's just that how do you reach the people? And I realized on the radio in the UK recently, there's been quite a strong focus on ultra-processed foods and the damage they're doing to people in terms of obesity and diabetes and all of these things. And the fact that it's costing the NHS billions to treat type 2 diabetes. And if they could get rid, I talk to medical practitioners whenever I see them. I say, which disease would you most like to get rid of in order to make the NHS function properly? And they say diabetes. They spend all their time on diabetes. And, it's a no-brainer. We know one of the things you can do, stop people eating ultra-processed foods, for one, and get them back in an acceptable light environment. We know the answers. How do we make those answers known?
Well, personally, I think the pendulum has to swing. I think things have to get worse before they get better. The entire reason that I ended up, interested in all of this is because I got very, very sick and doctors couldn't help me. No specialists could tell me what was going on. So I actually had to go down these rabbit holes and figure out what the hell was going on. And fortunately, I stumbled upon, people who were talking about the light problem, all of these more esoteric ideas that made a lot more sense to me. The foundational things, beyond, I don't really worry about diet too much, which is weird because that's where I started out. I'm a nutritionist, but I think, it's not even close what's more important. Light is so much more important. And I think it's just going to take a lot more people to become dissatisfied with the answers they're currently getting. And, I see it every day. I work in a hospital. And just as a side note, my office has these horrible 4K lights, these LEDs that just really hurt your eyes, and all of the doctors' rooms have them as well. And I remember because outside in the waiting room, they're all 2700. And I remember saying to my boss, because he designed the suite, and I said, why the cool white lights in the rooms, and then out in the waiting room they're warmer lights. He said, well, they told me that the blue lights look more professional. And I was just like, and I wanted to tell him about, your work and how, being in a blue lit environment is, can make you go hypoxic, and it can lower blood pressure, and doing what we're doing in there with lung function testing, it's probably not a good idea. But it's very, I know what you mean. Like I'm struggling to get more people interested in it. Even, even friends and family, they go, that's very interesting, but then it's difficult for them to transfer that into actual habits, aside from me going around changing all the light bulbs in the house and giving my friends light bulbs and things like that. But unfortunately, I think things have to get worse before they get better.
And they will. They will.
Because
we've just seen the tip of the iceberg, I think.
Yeah, I mean, well, there has to be a tipping point at which, we start to go, well, hang on, diabetes is clearly more than just processed foods, because it can't explain the whole story. We would have figured the diet thing out by now. The reason the diet, like all of the literature in looking at what the perfect diet is all so terrible, and that's because it's not connected to the light environment. I think diabetes is much more a disease of bad light than bad food, personally. But yeah, I mean, how are we gonna convince people that that's a big enough player to really start looking at?
Has anyone looked? I mean, I think it would be an interesting statistical thing to look at to try and extract the real history of type 2 diabetes in the population, and also the real history of obesity, excess obesity in the population over the last 20, 30, 40 years, perhaps, and just see what the connection connection is.
It probably
Yeah, well,
tracks.
if you look at the one graph I have in there, well, that's showing the effect of change in spectral range.
Mm.
I got in more trouble with that graph than anything I've ever gotten in trouble with because, immediately, oh, that's correlation, that's not causation, and, all
Mm.
this other stuff. And that's
Mm.
really, I think, the core problem is that, and that's why, I mean, honestly, I've been trying to actually get a defined mechanism. When you talk about processed meat,
Mm.
well, if you look at it, that's high in cortisol. If you look at what we do with chickens, there's 33 billion chickens in the world, and they all claim, oh, we're hormone free. Well, we've inbred them enough to where they're in constant pain. So by definition, their cortisol level is much higher than what you would if you had a true, free range chicken. And in fact, that's one of the things that we found interesting. The people that are actually growing chickens are kind of interested in our technology a little bit, but from the standpoint of they're recognizing that they're elevating cortisol and they're looking for some other alternatives. And but it to me it is hard. I mean, I was absolutely ecstatic when Roger did a video on us. We got 3.4 million hits, all these doctors and nurses. But as you say, it's been very difficult to convince them that, hey, it's worth changing out that light bulb and putting in this one. Or maybe you should actually redesign the building to where you bring some near infrared in, and bounce it around the building rather than reflecting it all off. And that's the problem is that like I say, we've had 3 million hits on a video, and it still can't get through to some people. And I think that you also have to understand that the lighting industry made a bet. It made a bet that they could get rid of all this extra wavelengths and told everybody you're going to save you all this energy, and to now come back in and say, well, that stuff actually meant something, it actually did something, is a hard nut to crack in the lighting
Oh yeah.
industry.
Oh yeah.
You
Sure.
know, it you don't go back to your customers and sell them. And unfortunately, I see this circadian thing as being a pretty much of a diversion from getting down to the real. If you actually, I used to put up hay in Kansas, and you slept like a baby after you did that. I mean, you were out in the sun, you were doing exercise. Most of the sleep disruption issues, I believe, are not associated with we don't have the right color light. It's
Mm.
associated with the fact we haven't really pumped up our melatonin levels like you normally do. And that was one of the things that I think was so fascinating about when you actually start measuring melatonin and cortisol during stressors, like exercise and things of that nature. You see that they actually go up together and
Mm.
they work together, and the melatonin eventually causes the when you have how many times have you had somebody say, you know why do I feel so sleepy after X, going to the beach? If you look at those things, you'll find, and that's what the data shows, is that once you get up to a certain point, it takes a while for that melatonin to get out of your system. So immediately after, those various things, a cold shower, things like that, you're feeling, observationally, I would argue you're feeling the after effects of having this excess melatonin working its way out of the system. And, the fact that we don't stimulate that is actually a negative for the body, because at the end of the day, you're increasing the amount of free radicals that the
Mm.
body's having to deal with.
Can
So
I pose something to you both? This is sort of backing up maybe a little bit before in our conversation. You touched on absorption spectra of water, and obviously we are bodies of water. I sort of see life as the meeting point of light and water. I think they essentially dictate what life is on this planet. So what do you see as the role of water in this story that we're telling about light, in human biology?
Well, I put my 2 cents in.
Mhm.
I believe that water is the primary chromophore, or
Right.
whatever you want to call it, especially bound water. I mean, when you start looking down at the cellular level, we are composed of these 10 to the 13th cells that are surrounded by the interstitial fluids. And, you got 24 liters in the cells, and you got 11 liters in the interstitial fluid, and you got 5 liters in the plasma. And all those things, when we look at it optically, that's a very complex optical situation from the standpoint of you got this cell that has various absorbers in it, but in reality, most of the light actually just bounces off the various changes in refractive index and throughout the water spectral windows. And so that's how you get this distribution that Bob shows so well in some of his pictures. And to me, that when you start looking at it at that level, you start seeing, as I said, that at various absorption bands, you got free radical generation rates increasing. And so there's a lot of, I think water is, everybody's trying to look for a chromophore like cytochrome C or whatever. And all I'm saying is that water's doing a whole lot of stuff in there, and being used by the body. It just makes sense to me. And that's why I actually would argue that going out into even the longer wavelengths, as you can see from one of the pictures in there, yes, it localizes in the skin, but it's changing. If nothing else, it's heating that particular area and causing it to locally to have a much different environment than if you didn't have it. And so I don't know if that answers your question, Cameron.
Yeah, I mean, I asked Michael Hamblin whether he thought water was the primary chromophore, and he said no, it's cytochrome C. And I thought, oh, that's interesting, because I would think it's water, given that the vast majority of molecules in our body are water. But I see where he's coming from, but I thought for sure water has to be the primary one, given and you're right, it has several absorption spectra bands that dip out a little bit further into the infrared, if I'm remembering correctly.
I was going to say, have you ever looked at the absorbance spectrum of water from X-rays to long wavelength radio?
No, I haven't. But
I'll show it. I'll show it to you and change your life. Okay. I have to do it in my notebook. I'm sorry, because I could find this, but I'll do it in my notebook, and I'll put it there. And you see that the blue line there.
Yeah.
On the left-hand side is X-rays, and on the right-hand side is ULF. It's the wavelengths they use to communicate with nuclear submarines underwater. Okay.
Yeah.
And you see this huge dip in the middle, which we call the water hole.
Right.
And that's centered right in the visible. Okay.
Yeah.
And as you climb out of that in the infrared, you get more and more absorbance, obviously, in the vibrations and the rotations of the water molecule, and it remains opaque all the way through the whole infrared, submillimeter, millimeter, and centimeter wavelength radio. This is why you lose satellite TV when there's a thunderstorm, because the water is, we have to put our millimeter wave observatories on tops of very high mountains to avoid the water vapor. But this water hole that coincides with basically the visible and the near infrared part of the visible spectrum. It's the reason we have life. The light, it's a necessary condition that is transparent in the visible. And that bounds the transparency window on the long wavelength side, because the water bands increase very rapidly in strength as you go into the infrared. And then the things like heme start at 600 nanometers as you go so you're left with this window between the water and the biomolecules, which define the transparency window. That's what I think about it anyway. And I agree with you. I think there are things going on with water. I think the photons that are hitting the water bands, Schultz vest experiment was done at 940 nanometers, which is in it's in the strongest water band below 1 micron. So I don't know, that was not by design, that was by accident, but it still seemed to work.
I have to ask you, Scott mentioned, there's a difference between, I guess, what Gerald Pollack calls bulk water, and then there's cellular water, which is more commonly being called structured water, or, there's a whole host of different names it's being called. But is there a difference in the absorption spectra of biological water that's inside of our cells, and bulk water, like the water that might come out of your tap? Do they have different absorption spectra? Because I know the structure of this crystalline water has these hexagonal shapes that look like they almost like aromatic amino acids, where they're ready to absorb light. Is there a difference there? Do we know?
Who's going to answer that one, Scott?
Well, Gerald Pollack was a really nice guy, or is a really nice guy, but he got crucified over easy water. And, I think that slowly they're beginning to realize that there's something there. And I actually tried to do some optical measurements of it using some prism approaches, but never got any good results that made sense. I think that, the I think that it's really hard because there's so many people that want to crucify people when they're trying to discover. And so I have a personal problem with people, not being open to having discussions about all different kinds of things. So I guess is how I put it. Maybe it's because that's what I've been going through for the last 3 years. I mean, it's just, I think that we kind of shut down discovery in a lot of ways because people are being too hard on they want proof. Well, proof is a hard thing to actually pull off. And
well, I have a story here as well. I think Glen was interested in this idea of maybe in the same person. I can't remember the paper actually, but the idea that on very small physical scales, essentially the viscosity of water would change, and so the idea was what the ATP pump, the rotating ATP pump, was lubricated by this special water that was influenced by light or whatever. And it sounded like an interesting idea. I read the paper at the time, but I have a good friend from Durham who's a soft matter physicist, and very bright guy. He's an FRS, and he does all this soft matter stuff. And I explained this idea to him, and basically his reaction was rubbish. Forget it.
Yeah.
So I wouldn't let that influence me too strongly because of the ideas that you have. I try and be open to these, but there was a time when Glen used that as his main justification for working on infrared light, and I dissuaded him from putting too much emphasis on that because I thought it was interesting, but there was really no way we could easily address that and look at it ourselves. I don't think.
Yeah. No, I mean, to get back to your other statement about how we actually get people to pay any attention, I mean, unfortunately, a lot of it's going to boil down to if they start showing more and more correlation and causation with various diseases and behavior activity, things of that nature. And that's why I've spent much time trying to understand a measurable mechanism. And that's why I kind of ended up at melatonin and cortisol, is because they have a huge impact. It's well known that they have a huge impact. And here we're starting to show that it's actually, being affected by the near infrared component. And, what'll actually change people's minds is when some lighting companies get sued. So that unfortunately will be what it takes in order to get them to actually do something. And it's unfortunate because there's so much promise in the area that it's frustrating, I guess I'd say is quite honest.
I've seen some doctors suggest that there will be a time in the near future where these LED lights that we're currently selling will have cancer warnings on them. I'm not sure if that's in my lifetime, but it's true enough that it makes me concerned.
No, I was just going to say, I think that Bob makes the comment, and I think it's true, is you go and you explain to somebody that we took away 90% of the spectrum and we're putting it back. They say, that's a good idea. And here's the reasons why you should do it. And I tell them some of the reasons why you should do it. The public has very little, then they want to know how much it costs. And that's why we spent time trying to develop a light source that is economical and does what we say it's going to do. What I find fascinating is that optically, the effect of that should be most in children and women, because women have thinner skin than males. Children have you get more of the light deeper into the body. And that's exactly what we see. We provide the light and it has two modes. It basically allows you to operate at full brightness where it's got a 3-to-1 near infrared divisible. And then you can switch it to low mode where it's 10-to-1, where it's basically just a little bit, and people use it like a little nightlight. And over again, we're getting people saying, I sleep so much better. My kids sleep so much better. And I'm afraid that to some extent, that's more effective than trying to prove the science, And that's kind of what we're at the point we're at right now. We're just starting to say, here's what it does. Here's the spectrum. Here's what their spectrum looks like. It's not the same. This looks what sun looks like. And, try our light.
Well, firelight, yeah. Firelight is great. Yeah, of course.
Well, yeah. And the other thing I was going to just quickly say is that, the question comes down to by putting in the near infrared back into our light sources, it simplifies a lot of stuff. What are the extent? I was talking to one guy. They've spent $2 million trying to develop a circadian lighting system for a hospital, and it has like 15 different LEDs in it or something like that, and all these control systems and all that. And I'm saying, well, here, you just put the LED with the incandescent filament, and it simplifies the drive characteristics and all that, and it just does it naturally. And I'll sell it to you for $20. And it's frustrating because there's not really any practical issue associated with putting it back, because what happens is that you can simplify the design, and from a system level standpoint, you can get efficiencies that are comparable to what they're getting now, because every time somebody tries to extend the spectrum, be it add violet, be it add red, whatever, all of a sudden the great argument of 120 lumens per watt goes out the door, because if you want to add those parts of the spectrum, the LEDs are very not efficient as the filament is to go into the near infrared, but as far as adding those extra parts to the spectrum, you're essentially, it's kind of like the people that are putting red LED lights in for bugs and stuff like that. they're getting 30 lumens per watt,
Mm.
and it looks red. So I practically speaking, there's really no longer any real benefit associated with just providing visible. Because I mean, to honestly provide visible, you need more red, you need more violet, you need all these other things. And when the minute you try and add those, all the lumens per watt numbers go in the toilet.
Mm.
So
That's very interesting. So what stage are you at in producing these things? Are you marketing these things yet or not?
Yeah. We got a DC version. We have a lamp that we sell that, as I said, it's got two positions. It gives you a day and a night. And because quick little story, we did an installation down at Princeton University, and I was talking to one of the guys there, and he said, "Yeah, we put in all these color changing lights in our conference rooms, but we had to take them out because we were breaking out in fights over what color temperature they wanted." Because they could adjust it. We designed the thing to actually just, it goes from, as you dim it down, it goes from 3000 Kelvin down to about 600 Kelvin. And as it dims, it actually drops its intensity, and it's just a function of voltage. And so it's pretty straight.
Well,
yes, we are starting to market it. As Cameron will tell you, I'm good at science, but I'm terrible at actually getting a product out the door. Well,
we ought to get Glenn to get some of these so he can try them out. I think I'm not going to negotiate that, but Glenn can negotiate that.
Yeah, well, I mean, that they're available, and we're trying, as I was telling Cameron, we're trying to get the UL on the AC version. But even if I get the AC version, it's a 120 AC. So you guys over there and in Australia are difficult. So it's easier just to send you a DC version so that you can plug it in and be done. And he'll take up to 5 lamps or something like that. Or we actually have a version where you can actually plug in your existing lamp and just convert over to our bulb. And so I think that's what we're selling now. And we're starting to put it into some stores and things of that nature.
Well, it's a start, isn't it?
I would just like to point out we're talking about the NIRA bulbs, NIRA. And just so if people are hearing this and they're wondering what we're talking about, they're the NIRA light bulbs that Scott's making, that are, correct me if I'm wrong, but half LED that take care of the visible portion, and then half incandescent, run at a low voltage so as to produce plenty of near infrared to balance out all of the visible portion.
Yeah, and I like it the best because it also has zero flicker.
Yeah.
And that to me is important too, because I think it's all part of this stress component that people are getting. A lot of people are sensitive. I know one guy that he literally can't walk into some rooms when there's LEDs or fluorescents, and has done a lot of work to figure out that's the flashing. Even though it's small, it's enough to cause him problems.
Yeah, and I think it's important to point out sort of the story that you've been telling, that the broadband, the broader spectrum of near infrared is more important. There are a lot of, like you said, these red bulbs that are monochromatic, that after having spoken to you, I think it's a much better idea to switch over to something that's got a broad spectrum rather than monochromatic, for a number of reasons. One being that monochromatic light does have physiological effects, and some people probably won't respond very well to just red light or just yellow light. So I think having a nice light with plenty of near infrared that's going to mimic sort of a firelight is going to be the best option in all of those cases. And it's great because it's got the separate options for lighting, like you said, the 3-to-1 or the 10-to-1 near infrared to visible. So you can use it in different scenarios as well. I just think it's I haven't had the chance to try them out, but I imagine they're going to be probably the best option for people who are considerate about their lighting options at home and wherever they have light bulbs. I just think it's a really, really important part of the coin. I mean, you talk about you can't consider the circadian without the other side of the coin being the photons that are actually coming out, and what we need as well as what we need to minimize.
Yeah, I mean, for me, the broadband characteristic of the sunlight is very important. And I just, every time I turn around, I model something. Why is this going on? Why is light going down here? And then all of a sudden you start to see, well, that's why it's doing it. And, there's a physiological effect. I mean, like I say, it is the most humbling experience in the world to actually look at how much body has done, or how the elegance of which the body is designed to absorb and collect near infrared in these ways that nobody seemed to know. I mean, I think we were kind of like the first to really start showing how light propagates. And go
Have
ahead.
I told you IKEA? Do you know IKEA, the store, the furniture store? You don't have
Oh
that in
yeah,
you. You know
yeah,
IKEA.
yeah,
You know when you walk into IKEA store, they take you round this zigzag path, which goes for miles
yeah.
towards until you can get out at the other end. So you visit all the different products on the way. And this is the exact model we're talking about.
Yeah, you're right.
The products are the weak absorbers. They're only weak absorbers. They don't sell very much, but there are many of them. And the light goes in and it takes this long path through the store and visits the maximum number of products on the way.
That's a great way to put it.
It's a wonderful analogy for the transparent part of the body.
Yeah, and that's exactly what happens. I mean, and we have so many interesting tools now that they didn't have back. They Florence Nightingale did statistics to come up with the idea that everybody should be outside and get fresh air and all this other stuff, but she didn't understand the mechanisms. Now we're starting to have tools. There's this a really amazing paper by Yakimov, and where he actually used Raman microspectroscopy to actually show that the outer 50 microns of the skin are organized. It literally, you get the melanin is actually reduced and is actually bleached out of the outer 50 micron, independent of what your skin color is. And so we actually have this very thin transparent layer. And why does it do that? Because if you look at the absorption of 285 nanometer UV, B, which we need to break apart cholesterol, that it is actually it gives a 5x increase in the amount of a reduction in the absorption of 285. So what ends up happening is we have this little microreactor on the outside. It also happens to be where, when he did this, the measurements, he showed that cholesterol was localized in that same 50 microns. And so, you look at this, and then you combine that with the work from Hudson, you find that if you take keratin, the outer skin cells, and you actually look at what happens as a function of wavelength, you get a 6x increase if you expose those skin cells to the entire solar spectrum, not versus UV versus visible.
Mm.
And so what you find is that you get this hydrogen peroxide component that comes out, and what happens with melanin? You have white hair, I have no hair, but the bottom line is that hydrogen peroxide is very good in combination with light for bleaching out melanin. And so there's all these little things that are going on in the body that we had no idea were there before, and yet we have the ability. It's like you were talking about blue light. NanoLive has this amazing holographic microscope. I forget how to call it, but it basically allows you to watch live cells while they're being exposed to light. 480 nanometers. Guess what happens when you expose a live skin cell to, or a fat cell to 480 nanometers? The mitochondria stop moving. And, but if you expose them to 635 nanometers, they actually are just fine. They don't have a problem. So there's all these things that we've got going on now that we can look at and we can say, wow, that's kind of interesting. What's going on? And
I'll give you another example of that. I don't know. There was a paper from the people in Bristol, just down the road from me. These are botanists, and they were studying. Cameron, we may have talked about this in a previous discussion. I don't know. They were studying iridescent begonias in the Malaysian rainforest, and these are deep under the canopy, and they only got green light coming down. Well, obviously they got infrared as well, but in the visible they only saw green light, and they found that the leaves were blue iridescent, and they were trying to understand why. And when they looked at the structure of the positions of the chloroplasts and so on, and they found that there was a layered nanostructure with a separation of about 150 nanometers, something like that, which actually trapped the light in a resonant structure where the antinodes were where the chloroplasts were. So they were taking the green light and trapping it in such a way that you interacted the chloroplasts with the antinodes of the standing wave to increase the efficiency of photosynthesis, to use the green light effectively. It's a very, very nice paper.
Always amazing.
A lot of detail, and
I'm just always amazed at the elegance of nature. It just is absolutely amazing.
I was going to say, I don't know if you guys have heard of John Ott, but he used to do all the time-lapse photography for Walt Disney, and he was made an honorary professor or something at whichever university he was collaborating with, and he does like an hour documentary on YouTube of a lot of his work, and there's footage on there of him putting chloroplasts on a microscope slide and then putting different color filters over the light and seeing what happens inside the chloroplasts. And it's fascinating to see what different colors, what different wavelengths do to the activity inside the chloroplast. And this was, I don't know, God, this would have had to have been the 60s when he was doing this. He very, very quickly realized, and he didn't know why, but he realized that full spectrum meant everything for biology. And to grow these plants and film them in a time-lapse manner, he had to get plastic that transmitted UV on the top of his greenhouses to grow, because he couldn't grow several plants without the UV. So it's kind of tying into what you're talking about with the different wavelengths doing incredible things in both animal and plant biology.
Well, and I think that over and over again, you see that, the body isn't trying to optimize for one thing. It's trying to survive from multiple different angles, multiple different things. So, the solution, like picking one particular aspect of light or whatever, is in my opinion, foolhardy in some ways, because the body does an amazing different, like I say, if you look at the idea that there is some kind of a photo bleached region on the outer part of the skin that everybody has, that's transparent at 285 nanometers, that's one aspect of a whole lot of other things. And I like Bob's comments about blue and red needing each other, and I would argue it's near infrared, but we can argue about red. But
I actually, that's a very interesting point, because I still puzzle about 670. What's 670 doing? But there is a chlorine at 670, which you find everywhere. It's ubiquitous. You find it in cheese rinds, you find it in eggshells, you find it in your poo and bird poo and everywhere.
Yeah.
And I don't know necessarily. I think I know which one it is, but I've not ever seen it identified. It fluoresces at 675 nanometers, and it fluoresces at 680 nanometers, and it absorbs at 675 nanometers. Yeah,
Yeah, but
and
I mean, to your point, there's a lot of that's really one of the frustrations with a lot of these tests and things that you try and run is, a lot of times you get a 10% or a 20% change. That's why I think that I make the argument that what we're looking at is we didn't do that. We took everything to zero. I mean, for a lot of people, there is no near infrared in their lives. For a lot of children, they do not go out and play outside. They go inside under artificial lights to do their stuff, to do even sports. And that is such a monument. I keep on saying we are literally living through the largest reduction in solar exposure in human history. You know, and what effects it's having.
in the history of the planet, actually.
Yeah, you're right. To me, it is, and what's crazy is that we never noticed, because everybody just responds to the visible portion and totally ignoring the fact that we totally wiped out all this other stuff. And so
we do respond to the lack of near infrared. We just respond with disease.
Yeah.
Yeah. I think that's a valid way to look at it. And it's frustrating because it's so easy to put back.
I don't know what's like in the States or Australia, but certainly in Europe, it's illegal to sell tungsten filament lamps.
Yes.
Now.
Yep.
Yeah. I think it's everywhere.
Yeah, but what it is that we use the little microfilaments. What's amazing is that it takes very few little filament lamps to generate significant number of optical watts in the near infrared, because they're essentially 100% efficient at doing it. So we're considered a hybrid, and we're actually not under that ban.
Okay.
So, and it's just what I am under is the fact that everybody thinks that an LED is okay. So,
while we were talking about UV light a little bit, I mean, obviously it's on the other end of the spectrum in the invisible side. Last time I messaged you a few months ago about melanin, and I asked you about melanin being a semiconductor, and you said yes, melanin is a semiconductor. I've been thinking about that quite a lot, mostly because I have no idea what the implications of that might be. I don't know whether you've read the work of Robert O. Becker, the orthopedic surgeon from Syracuse, who was looking into the DC electric current that runs throughout the body to regulate wound healing. That's what he was interested in. And he was very interested in the fact that bone in particular was a semiconductor. It had the collagen apatite matrix. One was a P and one was an N-type semiconductor. And that helped regulate the DC current that healed bone fractures. And it got me thinking, we've got melanin sort of all over. Is that playing a role in this DC current that's regulating, cellular processes?
You want me to take it, or you want it, Bob?
I'm not going to take that either.
Okay, I'll take it. Well, if you look at it from an optical standpoint, and look at how melanin is distributed in the body, particularly on the skin, there is it optically. And I show this in one of our papers. Is the texture on the epidermis at the epidermis layer, where the melanin is mostly located, is very equivalent to what we do in solar cells to actually increase their efficiency. And may or may not be the issue there, but it is optically, it's very fascinating that the body, most people think of the texturing that's going on at that interface as being a reason to for mechanical strength, but optically it localizes sunlight right in the region where melanin particles are maximum, and you've got an interface. So you can argue that there may be some effect there. There has been work done here down at Temple where they've actually taken melanin and created solar cells out of them. And so it actually does work, whether or not the body's taking advantage of it. I think a bigger issue with melanin is that for us, the reason we use a 3-to-1 near infrared to visible is that, to my knowledge, we're probably one of the only people. We actually measured people with high melanin content and looked at what it takes, especially in the near infrared, to how much energy is transferred through people that have 40% melanin versus 5% melanin.
Mm-hmm.
And it was absolutely fascinating that if you look at it between 600 nanometers out to around 1100 nanometers, it's about a 3-to-1 difference. The amount of energy, the amount of photons that would have to be provided to somebody who has dark skin versus somebody who has light skin. And, to me, it's just absolutely fascinating that we have so much issues associated with the Black population, African American population at higher latitudes in Chicago's, and the vitamin D deficiencies. And it looked to us that we needed to have at least a 3-to-1 ratio to provide for everyone in the population. But then by the time you get out past about 1100, water takes over, and we all look exactly the same, as you can see in that one picture.
Yeah.
So, I would argue that, it just makes logical sense that someone who has very high levels of melanin is designed to operate in an environment that is much higher intensity. If I go to the equator and it's hang out, I end up like a French fry, but somebody who has much higher melanin level is able to handle it in an entirely different way. Now take that same and reverse it and put that person up at a high latitude with minimal amount, it can have I believe, some really negative effects. So, I keep on saying that the Black population needs a higher level of near infrared exposure compared to the white population.
Yeah.
So that's, I guess, my response to melanin.
Yeah, it's super interesting. I've been as it rolls over into summer down here, I've been trying to get my melanin up as well. And that sort of takes me to this idea of biophotons. I don't know if either of you have sort of looked into this this notion that all of our cells are releasing an unspecified ultra low UV sort of these very, very small. I mean, you need these photomultipliers to even pick it up. So we're talking like individual photons, as far as I'm aware. Have you guys looked into biophotons and what that might mean in the context of biology?
I took melanin, so you got to take this one, Bob.
Well, I can't take it directly, but I do know one of our colleagues, one of Glen's close colleagues, John Mitrofanis, actually is in Sydney, or at least he was in Sydney.
He's in France now. I've also spoken to him.
You know John, yeah, he's in Grenoble.
John, yeah.
I mean, he's an advocate of this, and I must admit I've never been entirely convinced, especially about the UV ones, because I don't understand where you get the energy to emit a UV photon from. If somebody could enlighten me about how you could do that in these noisy environments. But the other thing it did strike me, and in fact I sent him a copy of this paper. There's a paper, very nice paper about all the chlorophylls, bacteriochlorophylls and all the chlorophylls, where they looked at the phosphorescence from these chlorophylls. So you get the normal fluorescence you get in the chlorines, next to the resonance absorption. But also all these chlorophylls have a longer wavelength, like around 1 micron, phosphorescent emission. And that's playing a role somewhere, because it's illuminating the way the excited electrons actually propagate through the various paths down to the ground state again. But and I just wondered if, you know, these sort of 1 micron-ish photons at a very low level, but obviously can be measured because they've measured them in the paper. And I wondered if that was related in any way. But of course, these are low energy photons, not UV photons. Yeah. The UV photons I don't get how you can emit a UV photon.
Yeah,
but
I mean,
then maybe just I'm not clever enough, but
I don't really understand it either. The only place I read it was in a book called Light in Shaping Life. Very interesting sort of textbook style thing that runs through the history of how light interacts with life, basically. And they've got these amazing photos from photo multipliers where you can see the fingertips and like the tongue in particular emit these biophotons more than any other part of the body, and it fluctuates throughout the day. So yeah, I'm not really sure what to make of it. But yeah, I thought maybe you had heard of it. But yeah, I'm not really sure what to make of it.
I mean, we try and keep open minds, I must admit, but we tend to be influenced by our ancient education to think of, I need to know the mechanism beforehand.
Yeah,
very old-fashioned view, of course, but
yeah.
So I don't know, but
I saw you taking some notes as we were talking. Was there anything either of you wanted to sort of discuss a little bit further?
Speaking for myself, I'm totally knackered after 3 sessions today. I'm not sure I can think straight anymore. But I mean, lots of very interesting things come up, and lots of things I'm going to look at a little bit more. But right at the moment, actually, I mean, this is vis-a-vis of nothing, but I'm actually working on a review paper on Arctic visual ecology with an ecologist who works in Tromsø and Svalbard. And this is a result of our paper on the reindeer, the vision of the reindeer, or a partial result of that. And we're looking at the way animals behave in an Arctic light environment, which of course is not fundamentally different from any other kind of light environment, except for the length of the twilights, which can be obviously 24 hours a day, almost. But this is raising some other interesting issues about low-level lighting and what it actually implies. And the one thing I discovered by doing this has actually surprised me, because I was studying the way that the twilight fades as you get to larger solar negative solar altitudes. So between the 3 kinds of twilight: the civil, nautical, and astronomical twilight. And I made a lot of measurements myself down to sort of the darkest part of civil twilight, which I can do with ordinary spectrometers and radiometers. And then I connected with my guys in Paranal, in the ESO observatories in Paranal, who'd done a study of the twilights right down to darkness, to -18. And when I joined those together, I fitted my radiometric results in civil twilight with an exponential, the brightness as a function of solar altitude with an exponential. And it was a beautiful fit. In fact, the R squared equaled 0. Sorry, 1, no, not 0, 1.000. I didn't get to where it actually deviated from 1. And then I used those to calibrate my spectrometric measurements, which were only relatively calibrated. So I was able to fit those onto the same level. And then I got the measurements that were made with astronomical telescopes right down to much fainter magnitudes. And all of these fit on this single exponential right the way down until the sky tends to dominate, the starlight and the air glow and the zodiacal light, which is near the end of astronomical twilight. So you get 5 orders of magnitude of brightness of twilight, which perfectly fits a simple exponential law. I know it's a single process of sunlight scattering off the upper atmosphere, but it really blew my mind that this should be such a simple physical law. It's actually quite stunning. I can show you the diagram. This is if you see, these are the twilights up here. This is civil twilight, nautical, and the astronomical twilights. And you see all those measurements down there. 5 orders of magnitude, they all fit on that straight line, which is an exponential. And then it curves up at the bottom where you start seeing the starlight and the other low-level sources of light in the air glow. I thought that was really cool.
Nature is amazing.
They have done some simple physical modeling of the twilights, and it does kind of follow that kind of law. But the fact that I just fitted it with a simple exponential in Excel and it straight through all the data, I thought was really cool.
I like things like that. Yeah. It does bring up the issue that I think that, is getting more and more attention, which is the artificial light at night and the effects of it. And, that's, to me, one of the prime drivers is the fact that we came in and developed these light sources that are essentially cheap to run, that would only provide visible light. And, it's created this behavioral, some things are driven by science, some things are driven by behavior. Like my neighbors, they put this most awful outdoor light in that they can't dim. And so it's on all night and it's blue almost. And, I guess my argument is that in some ways the LEDs are not only bad for us personally, but for everything else, not because blue light is awful. It's just, it's so easy to put it everywhere. And
the bright lights are not helpful for security because you can see much more in dim light for security than you can in this glaring light.
Yeah.
But, the point is that the artificial light at night has removed 5 orders of magnitude of visible light that you can see with the naked eye with a dark sky. So it's lopped 5 orders of magnitude off the 9 orders of magnitude your eye can see. It just lops off the bottom 5 orders of magnitude, which is
But
crazy.
I mean, and what's crazy about it is that the DOE did this effort, pushed this so hard because they were trying to save energy. We haven't saved hardly any energy because what's ends up happening is that people put more light bulbs more places, and especially at night. What are they saying? It's increasing by 10% every few years from the space station, when they're measuring. And it's not only increasing based on the intensity or the amount of output, it's also shifting to the blue, as Bob's case is being given. It to me, that's where everything is kind of coalescing around the same issue. Having visible only light sources with high efficiency is a bad thing. It's not a good thing. And the reality is that it's affecting our health. It's affecting the insects. It's affecting, plants. It's affecting all these different, animals. There was a really cool study where they took a bunch of scorpions and spiders, and they put them in 2 containers. One that was exposed to sunlight, one that was exposed to visible only light, and happened to be fluorescent, I think, at this particular point. And they not only ran through this for 14 days and then measured cortisol levels and saw a huge spike in cortisol, but they also observed that during the 14 days, the ones that were under the visible only light never came out of their burrows versus the ones that came out of natural light. And I think that the behavioral aspect of what we're doing is almost as important as the physiological changes that we're doing. You know, you got bird kills coming into the all these buildings, millions of birds. And, we need to start taking into account that it's not just, does it make me sick? It is, does it make other things not work well?
Stops in breeding as well. Stops insects breeding, stops firefly breeding. I mean, obviously. And so, yes, it is a disaster. And we have to make a major change.
Well, my concern is that everybody's running to, oh, we're going to put up a bunch of red lights. Number one, it's inefficient to do it. Number two, you really just need to turn off the light. It's not that complicated. But in our neighborhood, up lights on every house to make them look pretty. And now that they're doing it with LEDs, they have a whole lot more blue content. So to me, it's frustrating.
Okay. Looks like we've got a lot of problems going on, but I think we've come up with some pretty decent solutions as well. It's just a matter of getting more people aware of the problems and adopting the solutions. So I guess, like, from a practical point of view, the takeaways from all of this would be: get outside as much as possible. You don't even need to be directly in the sun. That's the beauty of being a bipedal, upright, hairless ape.
Sit under an apple tree like Newton did.
Exactly. You just have to be outside. You don't have to be directly in the sun. And be careful with light at night once the sun has set. It's really not. It's kind of more logical than anything else. You don't have to think about it too hard to go, well, that kind of makes sense. So I guess those are real takeaways, and who knows how much difference that could make to the health of everyone on the planet. So yeah.
And I would argue that we need to get to the point that we have some real hard studies associated with, what the spectrum really doing to us. If you look at almost every study out there, they'll compare fluorescent to LED. They'll never compare it to sunlight. And it's, yes, you can split hairs and say, I truly believe that, if you have a low blue content at night, it's better than having high blue content at night. But the reality is that's not what sunlight is, and it never has been. And we're messing around with the hormones, behaviors, and even some neurological issues. So, and they need to figure out how bad it is.
Well, we just did 2 hours, which is pretty damn good, and I'm sure we could have gone for another 2 quite easily. But for our own sanity, I think we'll cut it off there. I'm super happy with this. I've been really looking forward to it. I hope, I've been telling people, I hope you guys write a paper together at some point, so I can say, yeah, I got them together. I did that. But yeah,
we haven't disagreed yet, have we? I don't think. Not as far as I can tell.
No, I don't think we have.
No, no, it's been very clean. From the States to the UK to Australia, I don't know how we managed the time, but we got it all together. Yeah, I'm super happy with this, and hopefully people listen to it and get some good ideas out of it, and start to make some changes. It'll be slow at start, but hopefully with things like this, we can get there.
You should have the symbol of a random walk, because it's relevant to our discussion, but it's also relevant to the photons in the transparency band.
I will never forget the IKEA analogy.
Yep, I like that. And it's nice to meet you, Bob.
Okay, nice to meet you as well.
Thank you so much for listening, everyone. I really hope you enjoyed it, especially if you made it through the whole 2 hours. If you'd like to support Scott and Bob's work, I've left a few links in the description if you'd like to check out their work, particularly if you're interested in looking at Scott's bulbs, his hybrid incandescent LED bulbs. You're more than welcome to use the link to go and check those out. If you'd like to support this podcast, you can subscribe so you get notified whenever I release a new episode. I'd also like to encourage you to leave a 5-star review or give a thumbs up if you like the episode. This is a simple, no-cost way of supporting my work and helping me reach more listeners. Please feel free to leave any comments on my YouTube channel, as I do try and read through as many as I can. I've also put links to all of my social media platforms in the episode notes if you'd like updates about the podcast, information about health, or if you're just looking to reach out to me in general. Thanks again, everyone, for listening. Take care.